Hey everyone, welcome back to the Incredible India podcast series. I am Sam.
And I'm Taylor.
So imagine taking the invention of the radio, the discovery of the God particle, and even the math that makes your smartphone's GPS work.
Oh, and a Nobel Prize in economics, too.
Right, and tracing literally all of them back to one single staircase in Kolkata.
It sounds completely made up, but it's not.
It's really not. Today we're doing a deep dive into a really fascinating heritage trail guide from 5 census tours, and it uncovers how one specific building, Presidency College, which was established way back in 1875, basically incubated the modern world.
Yeah, we're talking about this Victorian Gothic building on College Street, and over about 70 years, it produced 6 world-changing scientists.
Which is insane. I mean, the sheer concentration of genius in just this one physical spot totally defies any sort of statistical logic.
Oh, absolutely. When you look at the source material for this deep dive, you quickly realize this wasn't just some random cluster of smart people who happened to live near each other. Right. It was this highly specific, totally cultivated intellectual ecosystem.
Exactly. All those massive breakthroughs we just mentioned, they lead straight back to the exact same classrooms, the exact same chalkboards, and, the exact same laboratories.
Which means our mission today is to figure out exactly what was in the water at Presidency College.
We really need to.
So I think we should start with the founding fathers of this whole lineage, the pioneers who kind of set the culture for everything that came later.
Yeah, because they weren't just running basic experiments. They were taking this incredibly rigorous scientific method and blending it with, deep philosophical traditions.
Take Jagadish Chandra Bose, for example. I mean, this guy was writing Bengali science fiction back in 1896.
Which is already super cool on its own.
Right. But then he decides to completely shatter the boundaries of biology by trying to prove that plants have nervous systems.
And honestly, that still sounds a bit like science fiction even today. But he actually proved it. He invented this instrument himself called the crescograph because, plants move so incredibly slowly that we just can't see it with the human eye.
It's totally imperceptible.
Right. So Bose builds this highly sensitive device. It used all these microscopic clockwork gears and a smoked glass plate.
Wait, like tiny watch gears?
Yeah, exactly. And this contraption was able to magnify the infinitesimal movements of a plant by up to 10,000 times.
10,000 times. Wow. So he wasn't just tracking that a plant grew a millimeter over a week. He was watching it react right then and there.
Exactly. He'd apply stimulus to the plant, so heat, cold, little electrical shocks, or even toxic chemicals, and the crescograph would record the plant's immediate physical shudder.
That is wild.
He essentially proved that plants transmit electrical signals through their tissues, very similar to how an animal's nervous system works.
He literally made the invisible pulse of a plant visible to the human eye.
He really did.
But, okay, if pioneering plant neurobiology wasn't enough for one lifetime, he's also the guy who transmitted the world's first wireless signal in 1895.
Yes, the radio waves.
But wait, I have to pause here and just ask the obvious question for everyone listening. Because if Bose demonstrated wireless radio transmission a full year before Guglielmo Marconi famously did it in Britain.
Right, the big question.
Yeah, why do our history books give Marconi all the credit for inventing the radio?
It was one of the great historical controversies of modern science, honestly. And it all comes down to the mechanics of the equipment. Specifically, this one component called a coherer.
A coherer.
Yeah. To detect an invisible radio wave, you obviously need a device that actually reacts to it, right? So a basic coherer was just this little glass tube filled with loose metal filings.
Okay, metal shavings in a tube.
Right. And normally those loose filings resist electricity. But when a radio wave hits them, they cohere. They basically stick together for a second.
Oh, and that lets the electricity flow through.
Exactly. It suddenly allows an electrical current to pass, which registers the signal.
So it's basically like an invisible switch getting flipped by invisible waves.
That is the perfect way to describe it. Now, Bose designed a highly advanced, super reliable version of this coherer for his 1895 demonstration. And the historical record, which our source material outlines pretty clearly, strongly suggests that Marconi later adapted Bose's specific coherer design.
So let me guess, without giving him any acknowledgement.
Not a single bit of acknowledgement.
Wow. Did Bose try to fight him on the patent?
He didn't. And that is where the whole philosophy of Presidency College really comes into play. Bose actually disliked the idea of patenting scientific discoveries for commercial gain.
Really? He just didn't care about the money.
He believed knowledge should be completely open and free for all of humanity.
Oh,
Yeah.
wow.
Whereas Marconi, I mean, he was really an engineer, but he's also a very shrewd businessman. He was entirely focused on commercializing telegraphy.
So Marconi gets the patent and all the historical glory?
Pretty much. But Bose's claim to the foundational technology is backed up by historical documentation that has never been definitively refuted.
So he basically open-sourced the wireless age. That's incredible. And like while he was doing all that, his colleague Prafulla Chandra Ray was teaching right down the hall.
Yes, PC Ray.
Right. And if Bose was kind of laying the groundwork for the future of physics and biology, Ray was building the architecture of Indian independence in the present.
He was a very different kind of scientist.
Yeah, he was a chemist, trained in Edinburgh, but he came back to teach at Presidency College. And he wasn't just mixing compounds in a vacuum. He looked around and saw an India that was completely, totally dependent on British imports for just basic survival.
Right, because the colonial economic loop at that time was incredibly extractive.
Extremely.
I mean, India had these rich natural resources and medicinal herbs, right?
Mm-hmm.
But all those raw materials were being exported to Britain, manufactured into actual medicines, and then sold back to Indians at this massive, ridiculous premium.
It's just a brutal system. But Ray recognized that true independence meant they needed economic and scientific self-sufficiency.
So he decided to literally short-circuit that entire colonial loop.
Exactly. The Heritage Guide notes that in 1901, Ray founded the Bengal Chemical and Pharmaceutical Works. So he didn't just write academic papers complaining about the problem.
No, he essentially birthed the entire Indian pharmaceutical industry.
Right from his lab.
Yeah, and he did it by applying the exact same chemical principles he was teaching to his students in his Presidency College classrooms. But what's truly remarkable is the personal ethos he maintained while doing it.
Yeah, I found his personal life in the sources to be just as compelling as his science.
Totally. Here's this incredibly prestigious professor and industrial founder, but he refused to adopt the Western dress of all his academic peers.
Right, he wore very simple, traditional hand-spun clothes.
He lived this life of severe frugality, and he funneled almost all of his considerable salary straight into student scholarships and the independence movement. Yeah, for Ray, proving that Indians could master and advance modern chemistry, that was an actual political act of defiance. He was showing his students that science wasn't just this abstract ivory tower pursuit.
It was a literal tool for national self-determination.
Exactly.
Well, it's one thing to challenge the British establishment with chemistry like Ray did, but the students who were sitting in those exact classrooms took that defiance and aimed it literally at the stars.
It is a perfect transition, really.
It proves this wasn't just a geographical coincidence, but a deeply cultivated chain of mentorship. So let's move to the next generation and look at Meghnad Saha.
Oh, his story is incredible.
It really is. His jump from a really precarious childhood in a rural village, growing up in severe poverty as the son of a shopkeeper, to eventually fundamentally altering humanity's understanding of the cosmos. It's just staggering.
It absolutely is. And to really understand what Saha accomplished in 1920, you have to realize what astronomy was like before him.
Okay, paint a picture for us.
Well, before Saha, astronomy was largely a descriptive science. Astronomers were essentially just making these giant cosmic scrapbooks.
Scrapbooks?
Yeah, like you'd look through a telescope, you'd map where a star is, and you'd note its color. But they had absolutely no reliable way to know what those stars were actually made of.
Right. When I was reviewing the material on the Saha ionization equation, the best way I could visualize it was like a universal barcode scanner.
That's a great analogy.
But I'm still honestly a little fuzzy on the actual mechanics of how it reads the star. Like, how does extreme heat turn into a barcode?
Okay, let's break down the mechanics. Think of an atom like a tiny solar system, right?
Mm-hmm.
You have a nucleus in the middle, and you have these electrons orbiting around it.
Okay, tracking with you.
Now, when a gas gets incredibly hot, like it does inside a star, the violent collisions between the atoms actually knock those orbiting electrons right off.
Oh, they just smash into each other and the electrons fly away.
Exactly. That process is called thermal ionization. And Saha was the one who figured out the exact mathematical formula that linked the temperature and pressure of a star to the specific number of electrons getting stripped away.
Okay, so the hotter the star is, the more electrons get knocked off. But how does that translate to the light we see all the way down here on Earth?
Right, so here's the trick. Because an atom that's missing one electron, absorbs light differently than an atom missing 2 electrons.
Oh, interesting.
Yeah. So when you pass starlight through a prism here on Earth, it spreads out into a rainbow. But there are these tiny dark lines missing from that rainbow places where the atoms in the star absorbed specific colors.
And those dark lines are the barcode.
Exactly. Before Saha, astronomers saw those lines all the time, but they couldn't decode them. Saha's equation provided the translation key.
So he basically allowed us to look at a tiny point of light millions of light years away and conclusively say, hey, that star is composed of hydrogen, helium, and iron.
Yes. He literally turned astronomy into chemistry.
He gave us the chemical composition of the universe without us ever having to leave Earth.
It's mind-blowing.
And what's crazy is that while Saha was doing that, his classmate, Satyendra Nath Bose, who, by the way, stood first in their exams while Saha stood second, was pushing boundaries even further.
Oh, S.N. Bose.
Yeah, the sources point out that S.N. Bose set a master's degree record at Calcutta University in 1915 that still remains unbroken over a century later.
Which is just a testament to the sheer caliber of the intellect inside that building.
Yeah.
But, it wasn't just raw intelligence with Bose. It was a staggering level of intellectual confidence.
You can say that again. I mean, fast forward to 1924. S.N. Bose writes this paper on quantum statistics. He submits it to all the leading European scientific journals, and they just reject it outright.
They didn't get it.
So what does he do? He bypasses the entire peer review establishment, puts the paper in an envelope, and just mails it directly to Albert Einstein.
It is an astonishing display of conviction.
Yeah.
Just, the journals don't understand my math, so I'll just send it to the smartest person on the planet.
Totally.
But, to be fair to the journals, the reason they rejected it is that Bose was proposing a completely alien way of counting particles.
Let's unpack that a bit, because quantum statistics sounds super intimidating. How is his way of counting different?
Let's use a coin flip analogy.
Okay.
In classical physics, if you flip 2 coins, there are 4 possible outcomes, right? You get heads, heads, tails, tails, heads, tails, or tails, heads.
Right. 4 distinct outcomes.
Because you can clearly track each distinct coin A and coin B. That's how classical physics treated particles like distinct billiard balls. But Bose realized that down in the quantum realm, certain particles are completely, fundamentally indistinguishable from one another.
Meaning you literally can't tell coin A from coin B. They are identical.
Right. So in Bose's math, heads, tails, and tails, heads aren't 2 separate outcomes. They're the exact same state.
So instead of 4 possibilities, there are only 3.
Exactly. And I know it sounds like a tiny semantic difference, but mathematically, it completely changes the probability of how those particles behave and clump together at really low temperatures.
And Einstein gets this letter in the mail, reads the math, and immediately realizes Bose has solved this massive puzzle.
Einstein doesn't just agree with it. He personally translates Bose's paper into German and submits it to the top journal himself with his own personal endorsement.
Wow.
And that collaboration is what birthed Bose-Einstein statistics.
But the part that absolutely fascinates me is how this abstract math directly dictates the physical reality you and I are experiencing right now, like the God particle.
Yes, the Higgs boson. Based on Bose's math, physicists realized that every fundamental particle in the universe is basically divided into 2 categories. And one of those categories is named bosons in his honor.
So what exactly makes a boson a boson?
Well, a boson is a particle that has an integer spin. You can think of it loosely like a quantum top that's spinning at a whole number speed. And because of the exact math Bose figured out, bosons are allowed to occupy the exact same space at the exact same time.
So they can clump together without pushing each other apart.
Precisely.
Which is why particles of light photons can travel together in a tight laser beam, because they're bosons.
Exactly. The photon is a boson. And so is the Higgs boson that was discovered at CERN in 2012, the particle that gives all other particles their mass.
That is just, wow. The very fabric of the universe operates on a statistical framework figured out by a guy from Kolkata who just decided to mail his homework to Einstein.
That's the perfect way to put it.
And that intellectual momentum didn't stop there. I mean, the rigor established by those founders inevitably commanded ultimate global recognition, bringing actual Nobel Prizes directly back to the halls of Presidency College.
Let's talk about C.V. Raman.
Yes. So he wasn't Bengali by birth, but he became the Pallet Professor of Physics. And he utilized the very same Baker laboratory that J.C. Bose had established decades earlier.
It really highlights the physical continuity of the space, doesn't it? Like the same walls, the same workbenches, breeding successive generations of discovery.
And talk about confidence. Our guide mentions this fantastic detail about Raman. He was so certain of his groundbreaking discovery in 1928 that he reportedly booked his steamship ticket to Stockholm to collect the Nobel Prize before he had even been announced as the winner.
That is bold.
So bold, but he was right. He won it in 1930, becoming the first Asian scientist to win a Nobel in the sciences.
Well, you can afford to be that confident when you've discovered the Raman effect.
So explain the Raman effect for us.
Okay, to understand why his discovery was worthy of a Nobel, imagine throwing a green tennis ball at a brick wall.
Okay, I throw a green ball.
The vast majority of the time, that ball bounces back perfectly green, with the exact same energy it had when it left your hand. And that is what light usually does when it hits an object. It scatters elastically.
But Raman noticed that the green tennis ball didn't always bounce back green.
Exactly. He realized that about 1 in a million times, the photon of light actually collides with a molecule and transfers a tiny fraction of its energy to make the chemical bonds of that molecule vibrate.
Oh, so the light loses a little bit of its energy to the molecule.
Right. And because the photon loses that tiny bit of energy, it bounces back with a slightly longer wavelength. So the green ball bounces back red.
Ah, so if the light bounces back with a different color, that color shift tells you exactly how much energy the molecule absorbed to vibrate.
Yes. And because every single type of molecule vibrates differently, that color shift acts as a perfect molecular fingerprint.
That's the genius of it. So you can shine a laser at a completely unknown substance, measure the exact color shift of the scattered light, and instantly know exactly what chemicals the substance is made of.
Without ever having to touch it, cut it open, or destroy it.
Which makes it incredibly relevant today. I mean, the source material points out that the Mars rovers are equipped with Raman spectrometers right now.
They absolutely are.
We are currently using a phenomenon discovered in a Kolkata laboratory in the 1920s to shoot lasers at Martian rocks, looking for the chemical fingerprints of life.
It remains the ultimate non-destructive tool of discovery. It literally bridges 1920s optical physics to the modern space age.
Okay, so we've covered physics, chemistry, biology, and astrophysics. But the profound influence of Presidency College wasn't just confined to the hard sciences.
No, it wasn't.
That same analytical rigor was turned toward the human condition. So let's look at the economics department and introduce Amartya Sen.
A giant in his field.
But first, I have to mention this beautiful detail from the text. He was named Amartya, which translates to immortal, by the legendary poet and fellow Nobel laureate Rabindranath Tagore.
Which really emphasizes the tight-knit cultural and intellectual web of Bengal at the time. The arts and the sciences weren't completely segregated. They fed into one another.
They really did. But I do have to play devil's advocate here for a second.
Sure, go for it.
We've been talking about quantum mechanics and lasers and plant nervous systems. How exactly does an economist fit into a lineage defined by laboratories and physical equations?
It's a fair question.
Yeah.
But it makes perfect sense when you realize that Sen took the exact same demand for underlying truth that Saho applied to stars, and he applied it to complex societal systems.
Okay.
He didn't accept the surface-level explanation of human suffering. He demanded to see the raw data and the hidden mechanisms behind it. And specifically, he focused his lens on famines.
Right, his groundbreaking 1981 book, Poverty and Famine.
Exactly. For centuries, the conventional wisdom surrounding famines was brutally simple. People thought they happened just because of a sudden drop in food availability.
Like a drought occurs, crops fail, the food supply vanishes, and people tragically starve.
Right. It was viewed as an unavoidable natural disaster.
But Sen had personally lived through the horrors of the 1943 Bengal famine as a young boy, right? Where something like 2 to 3 million people perished.
He did. And when he went back later as an economist and actually analyzed the ledgers, the actual data, he found a terrifying discrepancy.
What did he find?
He discovered that during the height of the starvation, food was actually being exported out of Bengal.
Wait, exported while millions were starving?
Yes. The region hadn't experienced a critical drop in overall food supply. The granaries weren't empty.
So if the food was physically there, why were millions of people dying in the streets?
Because of a concept Sen developed called a failure of entitlement. The rural poor hadn't lost the food, they had lost their ability to command it.
How does that happen?
Well, during the war, massive military expenditures caused extreme inflation. The price of rice absolutely skyrocketed, but the wages of rural laborers stayed exactly the same.
So their money just became worthless.
Right. They simply lost their purchasing power.
So they were starving to death right outside markets that were fully stocked with food they just could no longer afford.
Exactly. And because they were marginalized colonial subjects, they lacked the political voice, the democratic feedback loop, essentially, to force the government to intervene, halt exports, or control prices.
That is devastating.
Sen proved mathematically that famines are rarely caused by a true lack of food. They are caused by economic shifts and a lack of democracy.
He essentially proved that a famine isn't a natural disaster at all. It is a profound political and economic failure.
And that is why his work is so revolutionary. I mean, it was a politically neutral, strictly data-driven insight, but the humanitarian impact was immeasurable.
Because if a famine is a policy failure rather than a lack of rain, it means it is entirely preventable through human action.
Exactly. And that insight completely rewrote how global humanitarian aid is distributed to this day.
It is truly staggering when you step back and connect all these dots. I mean, think about your daily life right now. The wireless networks connecting the devices in your home trace their mechanical roots back to J.C. Bose's coherer.
The GPS satellite system you rely on to navigate uses calculations deeply dependent on Meghnad Saha's stellar physics.
And the fundamental policies of global humanitarian aid operating in the world today are built directly on the theories of Amartya Sen. All of these massive pillars of the modern world trace back to the collisions of genius happening on the exact same staircases of one single building in Kolkata.
It really forces you to rethink how progress actually happens. You know, we have a tendency to view history as this vast, sprawling, disconnected web of events.
Right.
But occasionally the fulcrum of history, the exact pressure point where the lever rests to move the entire world, is remarkably concentrated. It can be a single Baker laboratory.
It can be two brilliant minds sitting at adjacent desks. They could never go alone.
It is a powerful reminder that genius doesn't spontaneously generate in a vacuum. It requires an incredibly specific, nurtured ecosystem.
Which leaves us with a critical question for you to consider. We love to celebrate the myth of the lone genius, right? The isolated visionary having a sudden eureka moment in their garage.
Oh, definitely.
But looking at the undeniable, explosive success of the Presidency College ecosystem, it really makes you wonder about the way we work today. In our current era of remote work, digital isolation, and totally fragmented academic departments, are we slowly engineering the serendipity out of science?
That's a great point.
Will a perfectly scheduled Zoom call ever truly replace the creative friction of two restless geniuses sharing a workbench in the Baker laboratory?
I guess we'll have to wait and see.
If you decide to travel to India, we have a recommendation. 5 Senses Tools organizes tours across India, which are immersive cultural experiences. You can email contact@fivesensestours.com. Note 5 is written as a numeral in contact at fivesensestours.com or WhatsApp to +919 845 677446.